This presentation is split into two parts. So we will do now the first part, roughly half of the presentation. Then there will be the coffee break. And after the coffee break, we continue finishing the presentation. So you're highly welcome to return after the coffee break back into this room so we can proceed with our findings. Not this way. So my name is Sakretz, I'm with Mercedes-Benz, and I'm celebrating 26 years working for Mercedes-Benz. And last year I celebrated 20 years working in AUTOSAR, on AUTOSAR, and with AUTOSAR. And I deliberately took this very old picture of the motivation, what AUTOSAR addresses as its main field of operation. And from this picture to this latest architectural picture we just saw yesterday in the presentations, and we have been discussing a lot about the topics here, the AUTOSAR methodology spans the whole timeline and supports all the various technologies that are required to make a vehicle operational with the AUTOSAR infrastructure. So we are talking today about content of the AUTOSAR methodology, and large parts of that AUTOSAR methodology of today's speech are defined in the system template, in the TPS system template documentation, which is defined as being part of the classic platform, because this is where the whole methodology started off. Then, because we are also talking about the adaptive platform, we will see parts of the TPS manifest specification, which is the adaptive platform extension to the methodology, allowing you to configure adaptive platform systems. And it is crucial to understand that the TPS manifest specification is not a standalone document concerning methodology. Large parts of the manifest specification for adaptive build upon the foundation laid by the system template and the software component template. And so you cannot understand most parts of the manifest for adaptive if you don't read up the corresponding parts in the classic platform documents first. Then there's this abstraction of the AUTOSAR schema. There is one important message I always like to emphasize when talking about AUTOSAR methodology. And that is, it is very tempting to take the schema as the source of all information. But just because something is possible in the schema from a syntactic perspective, it doesn't mean that it's actually legal from an AUTOSAR template specification. So there are many constraints and restrictions defined in those template documents which restrict the usage of what the syntax of the AUTOSAR schema actually allows you to do. That's very important to recognize that restrictions. And then you will find in those template documents, and I deliberately made it very unreadable, figures like that, because I want to make sure that in today's presentation, after we have gone through this story we are talking about now, you will at least partially understand such pictures much better than you would if I just showed you this in the first place. So let's get started. And again, this is a very old picture from AUTOSAR 1.0 almost. And that was the motivation for how the AUTOSAR methodology is crafted as it is today. The virtual functional bus was always the idea that system design for a vehicle operating AUTOSAR systems in it should have at least a high-level knowledge of its applications software and the applications software communication needs. And this is reflected by having many software components defined, and the software components defining communication ports, and those communication ports communicating with each other to achieve the vehicle's functionality. And it's called the virtual functional bus because in its initial setup, it doesn't consider any communication technology. It's an abstraction. It just says it's idealized communication. All the software can just interact with each other. There are no networks, there are no network failures. You assume that communication always works. But you are already able, and we saw many presentations throughout the 2 days, to simulate your functional software already on the virtual functional bus level without having to consider whether communication introduces further issues to it. That's something that will be discussed later. And based on that virtual functional bus system description from an application perspective, now this innocently looking bubble called system design comes into this picture. And we could have also put it as the miracle happens here. Because this is the crucial design step of the OEMs. This is taking your vehicle architecture, taking how many ECUs do you have in a specific vehicle project? Are they alternatives? Are they optional? How many networks do you have? How do the ECUs connect to those networks? What are your gateways? What are the speeds of your networks? All that stuff this is what is an input into the system design. And another input is, of course, if you have constraints on your system you would like to design. Because if you want to take over existing ECUs and you don't want to change those ECUs, then certain software already runs on those ECUs, and they also have a predefined communication behavior. And you have to respect that constraints when you take your remaining virtual functional bus, your existing hardware topology, and need to design your system in the end. That means placing all the software components up here into individual ECUs and deriving the communication requirements out of that placement. And this is what then is applied in this extract phase, where you now, for each individual ECU, take all the information that is required to build that ECU from a design perspective. And you put it into one set of ARXML descriptions here. And this is the information that you hand over to your tier 1 supplier, and he takes that in order to configure the basic software and the RTE and integrate the application software that is envisioned to be put on that ECU. And if you have a second ECU, you do basically the same. And the advantage of that approach is that it eases the individual development of all of these ECUs. Because if in your system design you recognize that you have an issue in the communication between software component 1 and software component 2, and they only communicate to each other, then you can update the extract of ECU 1, and you don't need to touch any of the other ECU's extracts. They can stay the same. But how do you know that? The only way you can know that is because you have a system design up here. You know the consequences of changing this one line here. The consequence of changing this one line means I can restrict my change management to ECU1. I don't need to involve other ECUs. I don't need to contact other suppliers to apply any change. Because this one change up here ultimately results in the change of this extract for that ECU. So that's one of the advantages of having such a system design, top-level system design approach. And the ultimate goal, of course, of having those ECU extracts here is to be able to configure the AUTOSAR basic software. Because it was never envisioned, and specifically we are talking here about the communication stack, because we are doing communication today. And it was never envisioned that any one integrator starts configuring thousands of signals in this view here, in the ECU configuration view. The idea is always that you have a system description defining your communication needs, and that system description is taken as the input to configure the whole AUTOSAR communication stack. And then only limited amount of configuration work has to be added to make it actually operational on your specific hardware in your specific ECU. And when we are talking about the methodology, then of course the same approach applies to the adaptive platform. In adaptive platform, we call the boxes machines, but also there we can place software in them, and we can impose a certain communication need on those machines. And again, the extract for the adaptive machines then can be used to configure the behavior of the communication stack in the adaptive software foundation implementation. So now we will take a step-by-step approach how the communication matrix design has been put into the AUTOSAR system template. And starting point was, as I said before, top-down. We want to enable the communication between software components. Software components in classic AUTOSAR use two means of communication. We have sender-receiver communication, which is more a data-driven approach, and we have client-server communication, which is more a call-response communication approach. And ultimately, the goal is to put all that communication means into signals which can be put on the network. So this is one aspect of the methodology, but we don't need to go into that because in the presentation today we start with having those signals. It's just important to know that the signals are motivated by their realization of communication of software components. And if we have those signals, then we need to map those signals onto a communication infrastructure. This is a very old picture from the system template again, and it illustrates us when we did the system template, we started with CAN, LIN, and FlexRay. These are the three bus technologies that were designed to be part of the system template at the beginning. So up here, this could be a LIN or a CAN network, and it's a bus. So everyone listens to everyone else. Down here, this could be a FlexRay, because FlexRay has this speciality of being a dual-channel operation possible. So we can configure for FlexRay two channels which are almost independent from the payload perspective. But for the remainder of the discussions today, we will focus on a simple network like a CAN or a LIN. And if we talk about what is happening on the network, so if you just would pull out the wire of the network, connect some measurement unit to it, you would just see frames. The frames could contain PDUs and signals. The frame is typically what is defined by the network protocol. So CAN frames look differently than LIN frames or flexray frames. So they are specific for the technology that you are using to communicate. But already PDUs up here, they are, from an AUTOSAR stack perspective, independent of a network. And a frame typically contains one PDU, unless you're in flexray. In flexray, you can put several PDUs inside one frame. But in general, you can always put several signals inside one PDU. So this is the communication looking at a channel. And if you measure on the channel, you don't know who sends the data and who receives the data. And that is the job of the communication connectors. This is still the representation. And now we are going to not ARXML, but we go to the model representation of this. So we have here our physical channel. This is our network. CAN, LIN, flexray channel A or flexray channel B. So for flexray, you would have two of those entities if you are doing dual channel communication. For CAN and LIN, it will be always one. And those triggerings here, frame triggering, PDU triggering, and signal triggering, they represent the occurrence of those entities on the network. So the frame triggering tells us that a certain frame, in our case frame 1, actually appears on that network. PDU triggerings tell us that that PDU appears on the network. That has the advantage that we can define the layout of our PDUs and frames and then assign them to a network. So down here, we define this is a frame, this is a PDU, this is a signal. And whether that PDU is transported only on that network, or whether it's also transported on other networks, this is defined by saying, okay, that physical channel has a PDU triggering, and that PDU triggering points to exactly that PDU. So we know that this PDU will appear on that network. And this signal will appear on that network. And of course, this frame will appear. And whether that information is sent or received by each of the individual ECUs in our picture, this is defined by what is called the communication matrix. When we started, even long before AUTOSAR, this was done in Excel. Now we are much better because our networks get much larger. So at some point in time, it's not feasible to maintain a communication matrix of a real-life vehicle ECU in Excel any longer. But this communication matrix tells us that that ECU1 connected to this channel sends this frame with its signals, and it doesn't receive frame 3, but it receives frame 2, but out of frame 2, only signal to 1 is received. So this ECU is not even interested in signal to 2 or to 3. And this is defined again in the modeling by introducing the communication connectors. The communication connectors are used to define for signals, PDUs, and frames the communication direction on a specific ECU. So each ECU defines for each network a communication connector. So we have one here, one here, one here, and then always dual tuples here. And the communication direction could be either in or out. I'm receiving data in, or I'm sending out data out. And the link between I'm receiving data and I'm sending data, and what kind of data do I send and do I receive, is performed by those triggerings here. So we already saw the triggerings because they belong to a physical channel. So we now know that these signals, produced and frames are communicated on that network. And we now see who sends them and who receives them. Because for each ECU, you will have a similar structure defined, telling you that that signal triggering is an in direction on my ECU, and another PDU is an out direction on my ECU, and so on. And that will conclude the first part of the session. So thank you very much for your attention. We will continue after the break with the second part that will continue elaborating how the classic platform communication matrix is established. And then we will step over to the adaptive platform functionality, and finally bring those two worlds together using the signal service translation. Thank you very much for the first time. Thanks again for joining this second part of my presentation about AUTOSAR methodology and signal service translation. So we will continue in analyzing how the classic platform defines the communication matrix representation. And at this picture, I want to take a short detour into some special cases for the methodology description in the AUTOSAR templates. And this is about the multiplicities defined in this model. So this model is UML, and these multiplicities indicate which multiplicity each of these transitions and aggregations and references can have. And starting from 2211 AUTOSAR release, all of the multiplicities in those figures you will find in all the AUTOSAR templates have a 0 there. So they are either 0 to 1 or 0 to star. And star itself is equivalent to 0 to star. That's exactly the same semantics in the AUTOSAR modeling. The background is that we don't want to specify statically in those models the various use cases there exist for the existence of references or aggregations. And I have pulled out one example out of this picture which illustrates such a constraint that applies on that model, which is not able to be expressed by a simple 1 having here, or a 1 to star. That constraint says the reference, so it starts here, A, signal triggering, this is this guy, shall only reference an iSignal port if the communication connector, this is this guy, that aggregating that iSignal port. So this reference from the iSignal triggering to the iSignal port being part of that communication connector only is allowed if that communication connector is referenced by this physical channel which has this signal triggering. So only if they belong to the same physical channel, the connector, the triggering, and the iSignal port, then this reference is allowed. And this is a constraint we can't express in a simple 0 or 1 decision in this picture. And that's why it's so important to read the system template and the manifest specification, because thousands of such rules exist in those documents which define the semantical impact of how the modeling shall be used. And honestly speaking, this is quite a simple rule. I mean, there are even simpler rules which just say it has to exist or it shall not exist. But this is already a reasonably complex rule, but you will definitely find more complex ones. So this is a good starting point to get you used into how such constraints are expressed in the template specification documents. So coming back to the communication matrix definition, we enter at some point in time in the actual communication matrix, which consists of our physical channel, all the ECUs that are connected to the physical channel, and the send and receive relationships for each frame, PDU, and signal on that physical channel. So I hope with the description or with the explanations I gave you, this setup of how the communication network is defined could be followed up. The next part is about talking about the payload we are communicating. So, what is a frame, a PDU? How are they composed? And the frame is defined to be composed out of one or several PDUs. So in this example, that frame would be a flex-ray frame. Because in the beginning of AUTOSAR, only in flex-ray we can put several PDUs inside the frame. And each PDU itself is then composed out of one or several signals. And those signals, they don't have to be aligned to each other. There may be gaps in the PDU definition, and you can later maybe benefit from those gaps and introduce at a later point in time another signal in this gap. And then you would be quite compatible in your network representation. So this is the hierarchical definition of frames PDUs. And in order to be able to define that, you need to know at which position in the frame does each PDU go. So this one is put at position 0, and this one is put at position 32. Offset is bit in that case. And the same applies for the signal definitions. So in the scope of each PDU, we define at which position the signals are placed into those PDUs. Again, offset is in bits. And it's a relative offset, because it's always from the perspective of the PDU containing those signals. So signal 1.1 starts at position 0, but also signal 2.1 starts at position 0 relative to PDU 2. Because the fact that PDU 1 and PDU 2 are put into this frame is none of concern for the definition of PDU 1 and PDU 2. PDU 2 could also appear in a completely different frame and used in the third and fourth and fifth frame in your overall vehicle definition. It would still be the same PDU definition. It would just be put into frames of different networks at different locations. Then, of course, you also need the size or the length of these artifacts. So a frame has a length in bits, each PDU has a length definition, and each signal has a length definition. Because from a classic AUTOSAR perspective, it was always important to use as few bits as possible to transport the information you would like. So for a Boolean, typically you just use one bit signal on the network. There is no need to use more bits if you just want to represent true or false. And if you have an integer value representing the values from 0 to 6, it would be full enough to use 3 bits to to represent that information on the network. And coming from CAN, traditional CAN with 8-byte payload, and LIN, also up to 8-byte payload, packing your information in an efficient way was quite crucial at the beginning of the communication matrix design definitions. And this is now the modeling representation of the information we just saw. So we have up here, down here we have our signal. And the signal has a length. Up here we have our PDU. It's an I-signal I-PDU because it's an interaction layer PDU, and it contains signal. Therefore the name is I-signal I-PDU. And this one has one or several signal to PDU mappings, and each signal to PDU mapping has a start position. So we are saying, in this PDU, at that start position, this signal is put into the message. So that PDU, this starts this signal at that position. And the same applies for the PDU to frame mapping. So we have our frame, it has a frame length. We have our PDU, it has a length information. And we have the PDU to frame mapping, which has a start position. So where in the frame does the PDU start? And then for both PDU mapping and signal mapping, we also have the NDNS definition, which defines the packaging byte order. How is the information put into their containers? So is it big endian or little endian encoding? And now, many years later, Ethernet happened to AUTOSAR. And with the introduction of Ethernet, the SUMIP protocol was introduced into AUTOSAR. And it is essential to be aware of that the SUMIP protocol, we always talk about SUMIP, but you at least have to distinguish three aspects of SUMIP. SUMIP is on one hand side, it's a network protocol, transporting packets on the network. But SUMIP also has a service discovery option to it. They are sort of independent. You can use the SUMIP protocol with or without the SUMIP service discovery. And the third aspect, and this is the most relevant for us today, is the serialization of data in a SUMIP serialized message. Because we saw up to now that for our traditional communication matrix definition, that's how I called it, we can put booleans as one bit. We can put U in 3s, we can use U in 5s, U in 6, S in 6, whatever. And we can put them in arbitrary bit positions into our PDUs and frames. But SUMIP has well-defined sizes for the base types that are put onto the network. And that means that for Boolean, SUMIP always uses 8-bit to transport the Boolean information. And the designers of SUMIP said it is much more efficient to check an 8-bit value, if it's true or false, than rather having to mask out an individual bit out of a byte array in order to figure out whether it's 1 or 0. And so the efficiency was more important for the SUMIP serialization protocol than the payload size on the network. And the respective sizes are more or less natural. So if you want to put an U in 3 on the network, SUMIP would use a U in 8 to transport it. And in the communication matrix, we saw it up to now, the placement of your data type into the signal layout is arbitrary. You can choose whatever layout you like. You can shift them around, you introduce gaps or leave gaps out, whatever you like. You communication matrix approach. Some IP has a rule set how the data structure, which your compiler sees, how your data structure is represented in a byte stream for the network transport. So it's always essential for some IP to know what is my data I need to transport. And if that changes, also my byte representation for the network will change. And these are two fundamentally different approaches how data representation on the network is formalized. And the implementation of these two is done either using the COM module in classic AUTOSAR or the COM-based transformer, if you need to use the transformer chain. And it's the SUM-IP transformer that implements the SUM-IP serialization rules. So, now, we'll step over to the adaptive platform. So, big change. We have introduced Ethernet in classic many years before the notion of an adaptive platform started. And now the adaptive platform was introduced, and the adaptive platform took the decision that from an application perspective, only service-oriented communication shall be provided as an API towards the application developers. And the service-oriented implementation is done using the definition of events, methods or operations, and fields. And the field is a combination of an event called the notifier and a getter and a setter operation. And for us here, or this is the definition of a service interface in the adaptive platform. A service interface has some semantical versioning with major and minor version. And it has a collection of methods. Each method has arguments, and it has a collection of events and a collection of fields. For signal service translation, only events and fields are required, because classic AUTOSAR already decided that methods are always serialized using the SUM-IP rules. Even on classic AUTOSAR, a method call is always serialized using SUM-IP rules. Therefore, this is the service definition that is our foundation for the signal-to-service mapping. Why do we need it? Yeah, because from the classic platform, we get that stuff here. We get booleans represented as one bit somewhere in a packed byte representation. But the adaptive platform only supports the SUM-IP serialization up to that point in time, a few years ago. And so the need for signal service translation, and the term is signal service translation, but it applies, of course, in both directions. So it's signal to service translation and it's service to signal translation. It's equally implemented. And the idea is, of course, that classic ECU needs to interact with an adaptive machine on a VFB-like abstraction layer. The classic ECU, typically, or that use case using CAN, with a packed PDU layout. The order is different, and the sizes are also definitely not to the 8-bit layout that SUM-IP serialization requires. But SUM-IP serialization, which the original serialization for the adaptive platform used to be, expects the SUM-IP serialization representation on the network. So somehow we need to make these two worlds compatible, or at least translation, perform a translation. And you can do that in two ways. One way is to perform this on a classic AUTOSAR ECU in typically what is called the gateway ECU. The gateway ECU is the ECU which connects the CAN with an Ethernet, and in there you receive the PDU, you go up to the RTE, you have an application of the component which receives the data out of this PDU and sends it again using the sub-IP serialization rules. So, and in the system template, there is a chapter talking about that classic AUTOSAR-based signal-to-service translation. So this application, which could do that translation, can be automatically generated out of the information that is provided in the system description. But this is not always easy, achievable, or possible, or it's well known to do that. Because if we talk about safe or secure communication, then doing the recoding, doing the translation inside the gateway ECU requires that ECU to become safety relevant and security relevant. Because you need to receive the data, you need to unpack it, you need to check whether it's secure and whether it's safe, and then you have to pack it again, recalculate a new security and safety information, and then send it out as a sub-IP serialized message onto the Ethernet. And not everyone is able to introduce such a functionality in a classic AUTOSAR gateway. Specifically in one use case where the classic ECU provides information, and that information is tunneled over Ethernet, and then again sent to a CAN to another classic information. And the main path of critical information is the one from the classic to the classic. This is your functional behavior. And the adaptive ECU here, this is just a parasite also reading that information, but he's not the main cause for that communication. He just wants to also participate in that communication. And it was one of the motivations to also be able to perform signal service-oriented signal service translation in the adaptive machine. So we want to be able to introduce a schema, a system design, where coming from the classic ECU, we go into a traditional AUTOSAR gateway. We don't consider any safety or security rules. We just take the PDU as it is and put it into an Ethernet sub-IP package. And we tell sub-IP, this is a signal-based PDU. Don't look at it using the sub-IP transformer. This PDU cannot be analyzed by the sub-IP transformer, or it will be gibberish if you try to read that information. And that PDU is then received in the signal service translation, and there, with the knowledge of our communication matrix, which we saw before from the classic platform, we know exactly where each bit in that PDU is located and what it means. And signal service translation is now taking care of mapping our individual bits and partial bytes of our PDU, mapping them to the elements of our services, in this case, an event. And this is the model representation for this mapping. So on one hand side, we are saying, okay, it's a signal-based, we are in the signal service translation, event element. So we are talking about one element of an event. This event x1 has A, B, C, D elements contained. Two I-signal triggering mapping. So this mapping contains of two parts. One is a reference to that element B here, and the other one is a reference to the I-signal triggering of that PDU's element signal B. That's a signal-based event element to I-signal mapping, I-signal triggering mapping. And this is the communication part, the communication matrix part, which we already saw, with the definition of the I-signal as part of an I-signal PDU mapping inside an I-signal PDU. So if we know that information, this is already available in ARXML, we are able to derive what the signal-to-service translation needs to perform. And there are obviously also rules how that translation shall be done. And this is the switch which tells the system design that a certain sub-IP event is not a sub-IP-based serialization, but it is a signal-based serialization. So you have to have a signal-to-service translation mapping defined for that event in order to be able to analyze it. So, considering the requirements for the future vehicle architectures composed out of classic and adaptive AUTOSAR ECUs, still seeing many classic AUTOSAR ECUs in this picture, there is a substantial requirement to support signal-to-service translation. Because we will not be able to transform all our classic ECUs to use service-oriented communication. And therefore, defining or understanding the difference between these two worlds, and that's what I hopefully could transport today, it is essential that we are able to perform signal-service translation on one hand side in the gateway ECUs. This is a classic platform problem, not in scope of today's discussion, but also in the adaptive ECUs using the signal-service translation I just explained. These are the documents I have been using in this presentation. Mostly important the first two ones, but we already saw them at the beginning. And that's what I would like to thank you for your attention. And if you have any questions, we can do that in the coffee break, because I think we are running out of time. Anyways, so it's been an honor to present it again to you, and I hope you liked it as much as I did presenting it to you. Thank you very much.